Hello everyone, this is Brian Gao, and we are going to be discussing internal stability and external stability today of a system, which refers to the system's behavior in response to perturbations, whether or not they will converge to steady state or whether or not they will diverge from steady state, which of course corresponds to a stable and unstable system. So external stability refers to how finite changes in input result in finite changes in the output. It's also known as bound input, bound output. And internal stability refers to basically the tendency of a system to return to steady state after one or more state variables being perturbed. So internal stability, you can think of changing your state variables, and external stability, think of changing your input. So basically the idea here, the main purpose of this video is to explain this code. Basically it computes these values known as eigenvalues are going to tell you about the stability of a system. But before that, I just want to provide a little bit of a breakdown of what these values are. So let's consider the system, all right? And if we conduct first order kinetics, simple first order kinetics, we're able to write out this differential equation. In which case, if you go ahead and find the total solution after doing some Laplace transforms, this is assuming you have an input, you have initial conditions. We're going to have this kind of response right here. And the reason why this solution is very important is because it's basically going to show you what happens to these state variable over time. And as we can see here, this value here is the steady state. But what's particularly important to determine the stability of system is this value and this value right here. These are your lambdas, okay? These are your eigenvalues. And in this case, they're both negative k2. And negative k2, if an eigenvalue is negative, it means that it contributes to the stability of a system. So if both eigenvalues are negative, then we have a stable system. If even one eigenvalue is positive, we have an unstable system. Okay, so there are two ways of finding this lambda. The first way is, of course, just simply finding the eigenvalue of a linear system. Here's a little example. You're able to find the eigenvalues. So of course, in this case, we have, as we will see later, a saddle point, which is unstable. And the second way is by evaluating the transfer function. And the transfer function is made if you have zero state conditions. In other words, x of 0 is 0, but you're given an input. And so, as you can see here, the form of the Laplace transform basically becomes x of s is equal to u of s times h of s, where h of s is the transfer function. And so, what's important about the transfer function is that the denominator, s plus k2, this is known as the characteristic equation, and the numerator is known as the characteristic polynomial. All right, and the characteristic equation roots are known as poles, and poles are especially important because the poles, actually solving for the poles is the same as solving for the eigenvalues. Both of them tell you the stability of the system. They tell you the exact same information. And so now we're going to go ahead and transition into looking at this coding and see how this program helps you assess the stability of a system. So this program allows the user to input the elements of a Jacobian matrix for a homogeneous system to assess the transfer function, the poles, which will, in this case, eigenvalues, but of course the eigenvalues correspond to the poles, so essentially evaluating the poles, and to evaluate the overall stability of the system to these internal and external perturbations. External perturbations are very closely linked to internal perturbations, in that an internally unstable system is also unstable to changes in your system inputs. In other words, external changes. So basically what's going to happen is we're going to be supplying elements of a Jacobian, and you're also going to be supplying initial conditions, and we're going to be provided a phase portrait and a time plot, as well as an arg-and diagram. Now it's important to explain what these are. We're going to, so let's go ahead and let's do a demo first. So let's first simulate just stable behavior. So here I have some test cases we're going to run. So -2, 0, -0.15. And -2 for -4. And so what this program does is it essentially takes these inputs from the user, and it's going to construct a phase portrait, a time plot, and an arg-and diagram of the eigenvalues for stability assessment. And so as we can see here, in the phase portrait, these figures, well, I'll talk about the phase portrait first. The phase portrait basically shows all possible trajectories of your state variables in time. And this can be conveniently explained on this graph here because we have S1 versus S2, or sorry, S2 versus S1. And basically the idea is we're basically setting up a whole bunch of initial conditions, setting up different values to parameters, and we're going to plot in this phase space the evolution and changes in S1 and S2. So the plotting of these many different initial conditions gives us the phase portrait. And basically these plots will help illustrate the transient behavior around steady state. And so it provides lots of interesting information. So for example, as you can see here, in a stable system, the plots of S1 and S2 will be converging towards steady state. And in this case, since we're dealing with homogeneous equations, it's important to define homogeneous. That means zero input. So if there's no input, we're actually just going to have a pretty boring, you could say, steady state value of just zero. So notice how all these plots, all these trajectories are converging to zero. That is what defines a stable system. Okay, so therefore, as you can presume, in an unstable system, these arrows will all be, going out, and this will not converge into a steady state in the time plot. So basically what this program does is going to provide these plots for you to really see the stability of the system in two ways, phase and time. And so these plots illustrate the stability of a two-species reaction network in response to these perturbations. And the right diagram, etc., yeah, you already know these. And so basically, yeah, these plots are generated using the user inputted Jacobian values in initial conditions. The program will also provide you the eigenvalues that they use. So as you can see here, -2, -2, that's how you can tell it's stable, because of negative eigenvalues indicate stability. And we also have an Argand diagram to plot these Jacobian eigenvalues for stability assessment. So that's also very neat. There's a little caption here. So let's go ahead and just let's run through the code now. So basically, we're going to do a number of imports first. So these imports are for scientific computing, plotting, and simulation of the time plot. We're going to inquire the user to put in some the elements of the Jacobian, and then we're going to ask for the state variables, and then we're going to construct the Jacobian with the user inputted values, and then we're going to go ahead and evaluate the eigenvalues of the Jacobian matrix. Now we're going to be using these Jacobian, we're going to be using the eigenvalues of the Jacobian matrix to assess the stability, right? This tolerance I'll discuss shortly, but first of all, let's begin with basically the different cases of what can happen. In the case of no imaginary components, if both of your real components of your eigenvalues are positive, you will have unstable behavior. If both of them are negative, you will have stable behavior. If one is positive and one is negative, then we have saddle point behavior. And saddle point behavior is especially interesting because what happens is the trajectories move towards steady state in one direction called the stable manifold, and this forms a stable ridge. And in all the other directions, the trajectories actually move away, which makes this unstable manifold. And because trajectories only move towards steady state if exactly on this stable ridge, these saddle points are considered unstable. So that is why you cannot have just one positive and one negative eigenvalue. Both have to be negative to be stable. So, and then in the case of having imaginary components, we see here that we can have center behavior, unstable, and stable behavior. Let's talk about unstable and stable first before center. So in unstable spiral behavior, if the real parts are positive, the spiral trajectories move away from steady state. So your phase diagram will show the spiral trajectories going away from steady state. You may be wondering what the nature of the spirals are. And that's because what ends up happening is if you remember how the x of t is represented by this weighted sum of exponentials, if the exponent lambdas have imaginary components, if you use Euler's formula, you will notice that you obtain this real periodic function. And so that's what contributes to the oscillations and like the spiral natures. It's the sines and cosines that result from using Euler's formula and applying it. So that's how they work. And so in an unstable spiral, if the real parts are positive, the spiral trajectories move away from steady state. And in pure linear systems, these trajectories will expand out forever. And in the case of a stable spiral, that's where you have negative real parts. The spiral trajectories will move into steady state. So it's very cool, and it will end up becoming stable. And in particular, the center behavior, I had to use a tolerance. And the reason for that is the center behavior is where both you have imaginary components, but your eigenvalue real components are 0. And the reason why you need to use tolerance here is because due to the nature of coding, what happens is when you compute eigenvalues, they're not actually oftentimes computed to be exactly 0. They might be, for example, 1 times 10 to the minus 16. Obviously, that is not exactly equal to 0. So what we have to do is use a tolerance in order to say, okay, if it's within a small enough vicinity of 0, then it's basically 0. And this is done by simply doing these commands here, just comparing the absolute value of 0 minus the real component. If it's less than this or equal to this tolerance, then go ahead and call it centered behavior. And this is due to the problem with coding. It's called the floating point approximation. And then what's going to happen next is we're going to talk about the phase plot. So the phase portrait, or the phase portrait. What the phase portrait does is, in order to make this, you first begin with creating this dense mesh grid, and it sets up your state variables to range from -4 to 4, inclusive of the endpoints, by 100 steps. And the J just helps indicate the number of steps. What's going to happen is you're going to compute the derivatives at each of these steps for both the x and the y, in other words, the two state variables. And then what's going to happen is we're going to go ahead and plot using streamplot, which takes in the different state variable concentrations as well as the resulting differentials at each state variable value. So what we're going to do is we're going to use a streamplot to plot the phase plot, and then we're all done with that. These two expressions here just simply provide the horizontal axes, as you can see here, for visualization purposes. And then we have the time portrait. In order to do the time portrait, use Tellurium, and you load in this equation, and then you can simulate for some amount of time using the Tellurium package. In this case, it's simulated for 10 seconds. And then basically what's going to happen is you're going to go ahead and plot it. And this is here is just the caption for the plots. So this is basically all you really need to do to plot it. You're going to just be plotting the simulations on the plot. So that generates this plot over here. This is the caption that adapts to, as you can see, the user inputs over here, and that's described right over here. And then we also have an argand diagram of Jacobian eigenvalues. And to make this eigen diagram, we're going to make a function handle, actually. And basically what this does is it's going to iterate through the range of the length of the eigenvalues, which is basically a convoluted way of just saying, in our case, since we're just working with two state variables, 0 and 1. So for x, basically, and just for 0 and 1, we're going to be plotting the different eigenvalues, which, there's two eigenvalues, so that's what the 0th index and the first index indicate. And so we're going to be plotting these using red filled circles. And then what we're going to do is we're going to limit the plot. So if you notice here, we can't set like a defined axis for these because the eigenvalues can vary very heavily. So what we're going to do instead is we're going to make a sort of adaptable limit in response. So this limit will just help set us the axes, and it's just made by in accordance to the highest magnitude eigenvalue. And yep, and so this is basically the plotting of the argand diagram, and then we're going to actually call the argand function. And finally, we're just going to print out what the argand diagram provides you, so the eigenvalues and the behavior. Eigenvalues and behavior. So before we end, I'm going to go through two more simulations. We went through the stable one already, so I'm just going to present to you the saddle point and the unstable spiral, which I believe are the two most interesting ones. So 2, -1, 1, -2, 4, -4. So here we have a stable spiral. Oh, sorry, no, my bad. This is the saddle point. And in the case of the saddle point, as you can see, remember what I was saying about the stable manifold, there's only really like one case where we're going to be converging to the steady state. In all the other cases, the state variables are diverging from steady state. So because there's only one sort of this stable ridge, the saddle is considered unstable, and then that's also visualized in the time plots. And lastly, if we just go ahead and look here, we're going to be looking at the unstable spiral, 0, 1, -1.2, 0.2, oh shoot, my bad. So here we have an unstable spiral. As you can see, the phase portrait is diverging from steady state, and these oscillations are diverging from the steady state level. Again, that's because it is a linear system. If it's a nonlinear system, it may introduce some components to keep it from diverging. Otherwise, it's going to continuously diverge farther and farther away from your steady state. And again, notice how the argand diagram represents the eigenvalues on a visual portrait, and you can use these eigenvalues to assess the stability. All right, thank you so much for listening to this talk, and that's the end of this video. Thank you so much, and have a good one. Bye-bye.